All right, hello, and welcome to the next lecture video on acids and bases. And in this video, we're going to be looking at the qualitative analysis of acid strength. So let's just take, as an example, let's say we have HA versus HB. Now the question is, which is a stronger acid? In order to answer that question, we need to look at the reaction. And what is our acid-base reaction? Well, we have dissociation to give a proton and A minus in the case of HA, or a proton and B minus in the case of HB. Now, remember, we're looking at Bronsted-Lowry acids and bases. So the stronger acid will have equilibrium more on the product side. So let me just write that here. Stronger acid has, it's the larger Ka, the lower pKa, has equilibrium more on product side. What does that mean? It means the products are more stable. Well, protons are protons, so those are going to have the same stability. And what we really want to look at is the stability of the conjugate base. So we'll say more stable conjugate base. And let me just zoom in real quick here, just so that, there we go, that might be a little easier to read. So we can summarize by saying that to determine relative acid strength, compare stability of conjugate bases. The more stable conjugate base came from the stronger acid. So more stable conjugate base came from the stronger acid. Now, how do we figure out stability? Well, there are certain factors. So to determine conjugate base stability, the first thing that we want to do is look at the charges that may or may not exist on the conjugate base. So usually neutral species are going to be more stable than charged species. Oops. Okay, and just as an example, let me find a different colored pen here. There we go. If we're comparing H2O and H3O plus in terms of acid-base strength, we'll look at the conjugate bases we have OH minus, and we have H2O. So H2O is more stable. It has no charge compared to a negative charge on OH minus. That means that H3O plus is stronger acid. Okay, so that's the first factor that you can look at. There are some other factors that you'll also want to look at, and there's a neat little mnemonic for remembering those. So what is that mnemonic? So, all right, so we'll say if both conjugate bases negatively charged, look at following factors. And so what we're going to do is, the mnemonic to remember is REO. So it's kind of like the thing that opera singers sing in aria, except it's an O, REO. And REO stands for atom identity, resonance, inductive effects, and lastly, orbitals. So let's go ahead and take a look at each of these in turn. So first, atom identity. And what we want is, again, a more stable conjugate base. So with a negative charge, what kind of atom does a better job of stabilizing a negative charge? So more electronegative atoms, we'll say more electronegative atom stabilizes negative charge, but also larger atoms will stabilize, we'll say larger atom, sorry, stabilizes negative charge. And let's look at some examples of that. So just as an example, we can look at, let's do methanol versus CH3NH2, methylamine. And we'll look at our conjugate bases. And we'll remove the proton. And one thing you will want to get used to doing is drawing conjugate bases. So if I pull off this proton, this pair of electrons from the OH bond has to go somewhere. It ends up on the oxygen. Because remember, we're just pulling off the proton, the hydrogen nucleus. We're not taking any electrons with it. And so now we can look at our stability. And see that our methoxide ion has a negative charge on the oxygen compared to our conjugate base for methylamine, which now has a negative charge on the nitrogen. Oxygen is more electronegative than nitrogen, so the methoxide is more stable. And that means that CH3OH is the stronger acid. Okay? And just as a reminder, our trend is from left to right in the periodic table. And this is within a period or a row. And that becomes important because we want to compare apples to apples, not apples to oranges or some other fruit. And electronegativity is not the most important thing when it comes to atoms within a period. Within a group. It is the most important thing within a period. So if you're in the same row, in the same period, the more electronegative atom will stabilize the negative charge better. And again, the more stable negative charge, that's a more stable conjugate base. It came from the stronger acid. Let me move that over so you guys can get that there. All right. Now let's look at atom size. And I should actually call this E neg here for electronegativity. We'll look at atom size. And let's again take our methanol. This time we're going to compare it to something in the same group, so the same column. And that's thiomethane. And look at the conjugate bases. And once again, we've got CH3O minus. We'll compare that to CH3S minus. Now here, our CH3S minus is more stable. So the negative charge on larger S versus smaller O. And that means that CH3SH is the stronger acid. All right, and let me move that back up so you guys can actually see what I wrote. I do apologize for that. I also apologize for my barking dog in the background. You may hear that, you may not, I don't know. He's very protective. And anyway, I mean, from his point of view, you know, we haven't been violently murdered by the UPS driver yet, so clearly it's working. So we have our larger sulfur compared to our smaller oxygen. Even though oxygen is more electronegative than sulfur, here the size is what matters. And so our negative charge is on a larger atom, so it's distributed over a larger area, which means that it is more stable. All right, and again, our trend in the periodic table as we go down in the periodic table, the size of the atoms increases. And this is within a group or a column. And that's important, okay? You always want to compare things either within a row or within a column. You can't really compare things that are in different rows and different columns. That becomes tricky. For example, if I compared H2S versus HF, well, HS minus, S is a lot bigger than the F minus, but fluorine's a lot more electronegative than sulfur. So the electronegativity difference didn't matter, wasn't enough here, but it actually is in the case of HF. And HF is a stronger acid than H2S. So some of these are, again, you want to make sure you're comparing the same thing. So look at electronegativity within a row or atom size within a column, within a group. All right, so next we have, let's see, REO, so R, so that is resonance. And for resonance, more delocalization of electrons equals more stability. And a classic example of this is, of course, if we tried to compare acetic acid to ethanol, if we look at the conjugate bases, we have H3C, C double bond O, O minus. Now I can draw a resonance structure here. I'll go ahead and push my electrons in red. Push electrons there, push some there. And now that gives us H3C, C, O minus, double bond O. Like so. All right, let's put those in the resonance brackets. And we'll compare this to H3C, C, H2O minus. All right, so what we have here is a localized negative charge in the case of our ethoxide. But here we have a delocalized negative charge. In that the negative charge is spread out over both of the oxygen atoms. So the delocalized negative charge means that is more stable. Which means our acetic acid, here I've written it as CH3COOH, is the stronger acid. All right. Now, which is more important? Atom identity or resonance? In general, we go in decreasing order of importance. So usually atom identity is more important than resonance, but not always. For example, acetic acid is a stronger acid than CH3SH. pKa of this guy is around 8. pKa of acetic acid is around 5, 4.75, whatever. This is like 8.3. And so clearly this is the stronger acid. In this case, the delocalization is more important than the atom size. So there are always some exceptions. So usually you want to try to compare things that are similar. Okay? Is our negative charge on the same type of atom? Is just localized versus delocalized. In that case, delocalized is more stable, so that conjugate base came from the stronger acid. All right. Let's see. What is next? Next we have induction. So let me just leave that guy up there for now. And let's look at inductive effects. And with inductive effects, if we have electronegative atoms on, or let's say attached to nearby atoms. So electronegative atoms attached to nearby atoms can stabilize negative charges by induction, which is an electron withdrawing effect. So as an example, let's take a look at an example of this. And this is a rather extreme example. If we look at our conjugate bases with acetic acid, we have C, and I'm going to draw these in here with my wedges and dashes. H, H, C, double bond O, O minus. I'm not going to draw the resonance structures here because they would be the same. We have the same delocalization, so I'm not drawing. So I'm going to say resonance effects are not shown. And I'm going to compare that to my TFA, trifluoroacetic acid. And now what we see here is that the fluorine, because it's so electronegative, it will pull electron density towards itself. So we'll get a partial negative charge on the fluorines, which actually has the effect of pulling electron density away from the end of the molecule that has the negative charge on it. Okay, so we have a negative charge delocalized on those two oxygens, but the presence of the highly electronegative fluorine pulls electron density away from this carbon, which in turn pulls electron density away from this carbon and from the two negative oxygens. So it effectively spreads out the negative charge partially over a larger area of the molecule. So we can then write, let's write it this way. So we'll say negative charge partially spread out over larger area due to induction, which means that it's more stable, which means it came from my CF3COOH is the stronger acid. Okay, so again, we look at what's different. Here we've got fluorines versus hydrogen. Those are more electronegative. They help pull some of the electron density and spread it out over more of the molecules. So our CF3COO minus ion is more stable than our acetate ion, which means that our trifluoroacetic acid is a stronger acid. And these effects are additive. And they depend on distance. So the closer the electronegative atoms are to the negative charge, the greater a stabilizing effect they have. So if I had a long carbon chain with my fluorines way at one end, those wouldn't stabilize the negative charge that much because they're so far away. They're also additive, and just as an example of additive, if I've got, let's see here, H3CCOOH, my pKa is 4.75. If I have one chlorine, so carbon with one chlorine, HHCOOH, my pKa here is 2.87. If I have two chlorines, my pKa is 1.25, and you don't need to know these. And if I have, Cl3C, COOH, my pKa here is 0.70. And so the more chlorines I have, the more electronegative groups I have, the more stable the conjugate base is, the stronger the acid is. Similarly, the more electronegative the electronegative atom is, the more stabilizing effect that will have. So for example, I don't think I have the pKa of trifluoroacetic acid on hand, but the pKa of trifluoroacetic acid is lower than 0.7. TFA is a stronger acid than TCA because the fluorine, being more electronegative, stabilizes the negative charge on the conjugate base better than the chlorine does, even though the chlorine does a really good job of stabilizing it. When we get down to these types of pKa's, we're getting into borderline strong acids. All right. Okay, let's see here. One last effect to look at, and that is orbitals. And the higher the percent S character in orbital that has lone pair, the higher percent S character in the orbital that has lone pair, the lone pair is going to be more stable. And the reason for that is that our electrons are more closely held. S orbital smaller than p orbital. Okay, so let's take a look at this as an example. We can look at C, H, 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 H. Okay, so I've got three different alkanes here. And I'm going to look at the conjugate bases. Let me back up. These are not three different alkanes. These are three different hydrocarbons. I have an alkane, an alkene, and an alkyne. Sorry about that. Let's look at their conjugate bases. I'm just going to pull off a proton. So I'll have H, C, H, H, C, H, H, lone pair, negative charge. Compare that to a C double bond. There's an H there, C, H, lone pair, negative charge. Okay, now what's my hybridization? I have sp3 hybridization on this carbon because I've got 1, 2, 3, 4 things. Here I've got sp2 hybridization, and here I have sp hybridization. So now my sp3 orbital is 25% s, 75% p. There's a percentage sign there. Here I've got 33 and a third percent s and 67% p. And here I've got 50% s and 50% p. Okay, and that's just, where our sp3 orbitals are an average of a single s orbital and then 3 p orbitals. So there are 4 of them. Each of them is made up 1/4 of an s and 3/4 of p. So we have less s character for our orbital that has this lone pair compared to this one, and especially compared to this one. So lone pair more tightly held by sp orbital. H, C, triple bond C, H. Oh, I should say this is more stable. Is stronger acid. All right, our lone pair is more tightly held, thus this conjugate base is more stable, so it came from the stronger acid. And I could actually look at pKa's, and my pKa's here it's around 50 for this guy. It's around 44 for that guy, and it's around 25 for that guy there. So you can see that the alkyne proton is a lot more acidic. It's 25 orders of magnitude more acidic than an alkane, 19 orders of magnitude more acidic than an alkene. And that's due to the different percent S character in the orbitals. All right. So just to sort of wrap things up here, very short summary. You'll want to make sure that you are comparing sort of like things. I often say compare apples to apples, but if there are too many factors that are different, that can complicate things. So just in conclusion, a couple of things to note here. There are exceptions to relative importance of factors. So, for example, CH3COOH, O2H is stronger than CH3CH2SH, just as an example. And then again, if there are many factors involved, it can get a little tricky. So I'm just going to summarize that by saying, look for what's different between conjugate bases. Okay? Do you have a difference in resonance? Do you have a difference in atom identity? Look for what is different, and that's going to help you out. All right? So, just to conclude here, you can apply these to qualitatively explain why a given acid is stronger than another one, or even to predict why a given compound may be a stronger acid than another one. All right, so that wraps up this video. And in the next video, I'll talk maybe a little bit about base strength. Until next time, stay safe out there. Bye now.